Okay. So where were we left off? So last time we did this proof of basically correspondence between 3-point Gromov-Witten partition function of Hilbert of C2, right? Basically, yes, Hilbert of C2, and then the quantum product on the Fokker space on the Hilbert scheme of n points on C2. So that was this reviewing kind of roughly the proof of Pandey and Okunkov and Pandey. Now today I would like to just also review this really nice paper of Pandey and Shanhua Sheng. And because they discuss the same thing, but for big quantum cohomology. And it is really nice, and it's conceptual, and there are plenty of things one can learn from. So let's go over that. Okay, yeah, these I talked about. Yeah, so let's just talk about higher genus quantum cohomology. Quantum cohomology of Hilbert of C2, or I use this notation. Yeah, well, you know, there are on, but in a funny. Oh, what did you do?
On the side, there's the
Oh, I
side.
see.
Yeah.
Oh, okay. Yeah, I was trying to. Yeah, okay. So let's do the review. We showed that. The sum, I mean, it was very rough actually and very fast review of that paper anyway. I didn't go through the very detailed analysis of how those guys actually matched their partition functions. But anyways, let's assume that we showed the statement, at least we discussed about it for 2 or 3 sessions. So I think that I take as the, and this was the 3-point partition function of genus 0 invariance on Hilb n of C2 with degree d and QD, and we showed that this matches with the trace of the quantum multiplication operator acting on these two classes in the Fokker space of Hilbert. And this we did equivariantly with respect to equivariant parameters T1, T2, and we matched literally terms with each other. And the key ingredients, actually the key point was that we realized that on Hilbert of C2, we have reduced Gromov-Witten invariance, and everything is basically need to be having positive evaluation in terms of the term T1 plus T2. So that was one of the things that indicated what to look for on this side or on that side. And Okunkov and Pandey actually matched these contributions on each side modulo T1 plus T2 square. So on this side, because we realized we need to match them that way, we use the subtorus to actually calculate these 3-point invariants. And then we had these moduli space of the stable maps, and T fixed ones are we call the T prime fixed maps. That was the subtorus. And then we had to look at 2 types of T fixed maps, the broken maps and the unbroken maps. Our moduli space was divided into connected components, parameterizing broken or unbroken maps. And then we realized that the broken maps had 0 contribution. Anyway, so we matched these things. And here for us, D was the 2 cycle, actually, which was 2 and 1, and the topological divisor class in the Hilbert. Okay, so this is what we did. Now let us extend this to higher genus. So let mu1 to mu r be cohomology classes indexed by partitions of n, the equivariant Gromov-Witten series of genus G is obtained the following way. So this is mu1, mu2. This is our pointed function in genus G of, by the way, do you want me to use Hilbert n of C2? Because this notation is a little bit awkward, right? So let us just use, because I don't like putting parentheses every time. So let's just put Hilbert n of C2. Maybe it looks nicer. So this is this series mu r Hilbert of C2 genus G degree D QD, which is an element of the power series in the formal parameter Q with rational coefficients. These are Gromov-Witten invariants. So now we would like to prove some statement like this eventually. But we are going to have R mark points and actually higher genus version of this thing. Not genus 0, but higher genus. To do that, let's just discuss some ingredients that the authors actually used to prove the statement, analog of that statement for big quantum cohomology. And by the way, this is based on work by Pandry Pandey and this time Schenk. So they did higher genus Gromov-Witten theory of Hilbert of C2. So you would like to realize this, and let's just talk about first cohomological field theories. So this is one of the ingredients. We would like to realize this identity in the sense of cohomological field theories for the Hilbert scheme. So let's talk about these. Cohomological field theory. What is that? So let K be an algebraically closed field of characteristic 0 for us. Then let A be a commutative K-algebra and let V be a K-module over this K-algebra A. Be a free A module. Free module over this K-algebra A. Okay. And we want V to be having finite rank. Okay, so now we want to equip this data with some bilinear kind of pairing. So we would like to define let define eta as V tensor V to the base algebra A be an even symmetric non-degenerate pairing. And we also need to have the identity element of V. So that's an free A module, and we would like to have identity element. So let's call that let 1 in V, okay, be a distinguished element. All right. Now, with this data of V and the non-degenerate symmetric pairing on V, V is on a free module over this K algebra A, together with this distinguished element of V, we can define something called cohomological field theory. So what is that? So with this, we can construct cohomological field theory. So what is that? First of all, let us write eta as eta ij with inverse matrix denoted by eta ij. Okay. Now, so a cohomological field theory consists of a system. I call this system omega. It's a set of elements omega gr such that 2g minus 2 plus r is bigger than 0. This is a system, and it satisfies certain conditions. And what are the elements where? So omega gr, such that omega gr, this is an element of cohomology theory of the compactified moduli space of genus G curves with R marked points, and with coefficients taking values in this K algebra A, commutative K algebra A, times dual of V, R full tensor product R. Okay? So in some ways, it's a way of associating cohomology classes on M bar GR to elements of V for R marked points on the curves. Actually, think about Gromov-Witten classes, for instance. That was very similar. So you had, depending on how many mark points you had, you would be pulling back cohomology classes to the moduli space of the stable maps and pushing them forward onto this moduli space, and that would give you a class, right? So this is exactly that. It's not similar to that, but it's more general to that. In fact, for Gromov-Witten theory, I will tell you what does the cohomological field theory mean. It has very similar description to the description of the Gromov-Witten class. So, okay. And by the way, eta basically tells you that the symmetric pairing eta actually tells you that there is a natural isomorphism between V and V dual. So we are using a V dual. All right, so remark omega gr. Okay, so maybe I say it stands for associating a class on M bar GR to elements of V, assigned to R markings. Okay, so that's what it is. Now, like grammar-within classes, the same way that grammar-within classes had axioms, cohomological field theories also have axioms. They need to satisfy certain axioms. And again, as you can guess, basically, these are somehow that when you specialize to grammar-within theory, they match exactly with the axioms of grammar-within classes. Okay, so this already gives you a lot of ideas that depending on what you choose for this one, you can basically produce many different cohomological field theories. So, cohomological field theory axioms. So one axiom is that each omega GR is SR invariant. Here is S is the symmetric group where SR permutes mark points and copies of V star. And this is the first axiom. So then we had axiom 2, which is gluing maps, exactly like how we did it for grammar-within classes. Gluing maps. So Q is a map, let's say, from genus minus 1 R plus 2 mark points to M bar GR. This is that forgetful map that we had before. And we can define Q tilde as the gluing map. M bar G1 R1 plus 1 times M bar G2 R2 plus 1 all the way to M bar GR. And then the gluing map actually tells you what happens if I take one of these elements of our cohomological field theory and I realize it. How should I realize it in the pullback, in the source of these two maps? So then the pullbacks Q upper star and Q tilde upper star are equal to so basically it would be contractions of omega G minus 1 R plus 2 and omega G1 R1 plus 1 tensor omega G2 R2 plus 1 by vector I and j a to ij ei ej, where this was the inverse of this non-degenerate pairing eta that we defined on V, on our 3-module V. So for instance, this is for us very similar. When we do grammar-within theory, do you know what this is similar to?
Which one are we calling? mean, this is the gluing theorem. I'm just trying to recall what that says. The GIJ.
Exactly. It's the intersection matrix. And for the Hilbert scheme, when we do Gromov-Witten theory of Hilbert scheme, again it will be some sort of intersection matrix, but the one that we define out of pocket space. Exactly. This is exactly that. Okay. Then we have the third axiom too, which is let V1 to VR be elements of V and P be a map from M bar GR plus 1 to M bar GNR be the forgetful map, then we require that okay. So we require these identities. So M omega G R plus 1 V1 all the way to VR times 1. We would like that to be P star, P upper star, omega GR V1 VR. This is exactly the condition that Gromov-Witten class is also satisfied. And omega 03, if you remind yourself, this we also had before. This was just the intersection, or for us, this eta acting on V1 and V2. This we also had before. It was one of the axioms, right? Okay, good. So this was when we were pulling back fundamental cycles in the Gromov-Witten class and just... Now, these are the axioms, the three axioms, similar to those we have seen before. And now, definition. A system omega equal to omega GR. Now I can denote it this way. 2G minus 2 plus R greater than 0 of elements omega GR as above, satisfying properties 1 and 2 is a cohomological field theory. That's it. If property 3 is satisfied, it's called cohomological field theory with the unit. So if 3 is satisfied, it is called cohomological field theory with a unit. Okay. All right. So similar to Gromov-Witten classes, cohomological field theories induce some notion of quantum product on the cohomology, and so we can talk about that. So a cohomological field theory, omega yields a quantum product, well, before our space on which this was inducing a quantum product was what? What was the vector space?
I mean the cohomology.
It was the cohomology of our variety.
Yep.
Here we have just defined it for a vector space V. So induce a quantum product on V. And basically it's defined the following way via eta of V1 star product V2 paired with V3 would be equal to omega 0 3 of V1 times V2 times V3. Well, this was again satisfied when we used instead of eta the G, and this was the property of the quantum, small quantum product actually. And this made our cohomology theory of the variety into a Frobenius algebra because it has two notions of inner product and it respects the metric because in fact this thing was the same as eta of V1 comma V2 star product V3 and was also equal to this thing. Okay, so that we have associativity of star follows from property 2 and the element 1 in V is the identity element for this operation of star by axiom 3. Exactly again similar to Gromov-Witten classes and a small quantum cohomology. Okay. All right, now a cohomological field theory, omega, let's call it. I would call it little omega instead of big omega, composed of only degree 0 classes. So that means that classes on the moduli of genus G curves, marked curves, those we want to be degree 0 classes. Basically, these will be little omega GR in H0 of MGR with coefficients in this algebra A tensored with V0R is called a topological field theory. That's a subset of cohomological field theory, only the one which is on which we are specialized into degree 0 classes in here. Now by axiom 2 omega GR of V1 all the way to VR is determined by considering stable curves with maximal number of mark points. Those are genus 0 curves, all of them. not genus zero curves, but there's some statement that this kind of field theory can be recovered from genus zero one. So considering the stable curves with a maximal number of nodes, and every irreducible, this is the one point I was trying to make, every irreducible component of such curves is a genus zero curve with three special points, Hence, the value of omega GR, the class, can be determined is uniquely determined by values of omega 0, 3 and this non-degenerate pairing eta. Yeah, so if you give me V and eta, then the topological field theory is uniquely determined. Okay, by the associated quantum product. Okay. Now, this is for cohomological field theories and topological field theories. Of course, now we know already that this is a specialization to Gromov-Witten theory, and it's not surprising at all that our cohomological field theory classes are very similarly defined as Gromov-Witten classes. So, the Gromov-Witten cohomological field theory is constructed from the virtual class of moduli space of stable maps. So the Gromov-Witten class, cohomological field theory class for the Gromov-Witten theory of R elements of V for R markings is defined, as we are not so surprised, by sum over all partitions, sum over all curve classes in second integral cohomology of your variety X, Q beta, rho lower star of evaluation upper star of product of these elements capped with m bar gn, or gr actually, x beta virtual. And what is rho? So evaluation map is obviously the map that sends you from here to R full product of X. And rho is the forgetful map from here to the moduli space of genus GR R-pointed curves, which contracts the unstable components of the stable maps and sends them to a stable curve. Okay. The only thing that we needed was that this vector space is given by certain cohomology theory of X, and that would precisely give us the grammar within class. Okay, so that is that, and here, now this is important, and we did discuss about this too. Here, A is the Novikov ring Novikov ring with Q coefficients. Given a certain, given as completion of group ring associated to semi-group, group ring associated to semi-group of effective curves on X. Effective curve classes on X. So our V is here defined by rational cohomology theory of X, tensored over Q with A. It's the free A module that became this way. That's the Novikov ring. We discussed about this, if you remember. When we were working with big quantum partition function, we discussed about all possible extensions of our cohomology ring because we had divergence issues and so on. Okay, and as it is expected, furthermore, eta is an extension of Poincare pairing. And 1 in our vector space V is the unit in cohomology. All right, so now we would like to discuss that with respect to this notion of quantum product. The V that we construct this way satisfies certain semi-simplicity property. We would like this to be a semi-simple algebra with respect to this product structure. So semi-simplicity let omega be a cohomological field theory. Well, with respect to the data V and non-degenerate pairing and a special point of element of V, define the R matrix R, an element of identity element 1 plus Z times endomorphism of V power series with coefficients and z times endomorphism of v in variable z. It produces for you a matrix satisfying what is called symplectic condition which is r of z times r star of minus z is equal to 1, or the identity element. And this is the adjoint of r with respect to this non-degenerate pairing eta. So adjoint of r, of course, with variable indeterminate basically replaced by minus c with respect to eta. Now this is that R matrix that we discussed before. For our computations, we use R matrix formalism. To compute. Okay, so this is R. Now, what happens is that R acts on the given cohomological field theory. I'm going to define an action of R on this cohomological field theory omega. And that induces a new cohomological field theory. And there's another action too. And these two actions actually give us, via a theorem by Giventhal and Telemon, they give us a classification of these cohomological field theories, or semi-simple cohomological field theories. So action of R on omega. Let's discuss that. A new cohomological field theory with respect to V eta and 1 is obtained via the cohomology elements. Cohomology elements R gamma which is R acting on gamma GR. Well, this is something that sees endomorphisms of RV. So in terms of the power series in Z, those are the degrees. And we can act on elements of V. Imagine that elements of V are given by cohomology classes of your variety. So it produces new classes and certainly new cohomological field theory.
Well, we have the parameter Z here, right?
Mm-hmm.
So if you feed in cohomological classes, what you get is a power series.
That's right.
So how do you get a new cohomological field theory? Like, you have to specify what Z is?
Mm-hmm.
Okay.
I will show you.
Oh, I see.
You need to, yeah, I will show you. That's right. So we are going to do it this way, actually. So this guy is defined as sums over stable graphs. Stable graphs, omega of genus G with R legs and R legs with contributions. I will tell you what this is. Contributions coming from vertices, legs, and edges. So, in one way of doing calculations in Gromov-Witten theory is using this graph theoretic description. So if you have some curve of genus G with R marked points, which could be a reducible curve, okay? So for each vertex of this thing, for each irreducible component, you recognize that as a vertex of this graph, and then you decorate the vertices with the genus of those irreducible components. If the two irreducible components are connected to each other by a node, then you can draw an edge, and then if the irreducible components are marked by some Ri many points, then you draw the legs. So, depending on how many mark points you have. You can label the markings as well. So you can call this P1, P2, P3, and something like that. And then, if you have some genus G stable curve with R marked points, then the total sum of the legs should be, of course, R. And you can distribute G's depending on what the structure of your curve is. So this is what it is. And now I'm going to tell you what is this cohomological field theory? How is it obtained? It's obtained as sum over these stable graphs. And there's a notion of a stability, actually a stability of stable map moduli space, or a stability of the, M bar GR, actually has a translation in graph theoretic sense as well. I mean, there is one. So this is given as a sum over these stable graphs the following way. So the system of new classes is given by sum over all possible stable graphs, 1 over automorphism of those things, I gamma lower star of contributions of vertices times contribution over edges of edges times contributions over legs. And I now need to tell you what these are. Okay. So this is the embedding of a particular moduli space of. So for each stable graph, you're looking at a certain component, and that gives you an embedding inside the moduli space. And so what does the contributions now mean? This vertex contribution, that's just omega G of V R of V with G of V and R of V denoting the genus and number of half edges and legs on that vertex of the on that vertex. Number of half edges and legs on that vertex. Right? This is obvious, right? We have defined omega GR. We know exactly what it is. And we look at a particular vertex. And this is a curve of given genus and some number of mark points on it, hopefully, or probably. And then you can construct it. So that is that. And then, actually, I have myself done some, as an examples, and when I was trying to learn this thing, I was done some computation. So basically finding out what some of these certain classes are. Combinatorics is really horrible, actually. When you actually write down something for a very low, actually, even low, let's say genus 1 or something, with low number of mark points, you just realize the number of stable graphs could be more than what you think. So often computation with these stable graphs, at least by hand, is kind of difficult. Yes, but I think people are writing codes for these, and there are many people who are really good in this. It is helpful actually to try to compute some of these. You have some certain axioms of stability, and you just distribute basically the mark points and the genus over your graph and see all the possible combinations. To the contribution of legs that is given by R psi L. These are also cohomology classes, and where psi L is the cotangent class at the marking corresponding to legs of the, corresponding to the leg, to that leg, to the leg. So you have some irreducible curve of genus G, some genus and some number of mark points. At those mark points, you can look at the first term class of tangent or cotangent bundle of the curve at that point. That gives you a cotangent class, and that's basically what it is. That's how it's defined. And then that's an element of your vector space, and you can act by this endomorphism on it. Three, the edge contribution is defined as follows. So contribution of edge is equal to, this is a little bit eta inverse minus R psi prime of E, eta inverse R psi double prime of E T. Psi prime of E psi double prime. Again, this is an edge. You have a node, right? And it connects a genus G to a genus G prime irreducible curve, and then you can calculate these cotangents. So here, psi prime E and psi double prime E are the cotangent classes at the nodes that represent the edge E. So that's a node, but then on this side and on that side, it's a node of those irreducible components. You can calculate the cotangent bundle of that at that point. You can calculate the cotangent bundle of the other component at that node. And you get these psi classes. Okay. So this is the new homological field theory you get this way via computing edge and vertex and leg contributions. Now, this is an action of this R matrix, which produces for you a new cohomological field theory, and there's another action too. And having these two actions, we can state this given tall Telemon statement, classification statement. So let me talk about the second action. Consider a power series T in variable Z with coefficients in this V. Now let's think about V as the cohomology theory of X, with no terms of degree 0 and 1. So what does that mean? Your T of Z, that was R of Z, and this is T of Z now, is defined as T2 Z squared plus T3 Z cubed, where TKs are elements in V. This is some sort of the one I'm going to define as this T is acting on our cohomological field theory, and the action is kind of a translation action by translation. And new cohomological field theory with respect to V eta and this distinguished element 1 denoted T omega is defined by okay. This is defined by the following way, by setting T omega GR of V1 tensor to VR is equal to sum from 0 to infinity of 1 over m factorial PM log star of omega G R plus M V1 VR tensor with T of psi R plus 1 and the T of psi R plus N. Where P of M is from M G plus G R plus M to M bar GR, the forgetful map. Forgets M mark points. Okay. It's a translation.
What's your psi r plus 1 to psi r plus 1? What's your psi r plus 1, psi r plus 1?
Yeah, that's right.
What are those?
Those are basically cotangent classes again.
Right.
So now we are moving them, we are translating them. So, like in here, these T's are elements of V.
Right. So like those cotangent classes are taken where?
Yeah.
Like where? Like earlier, those cotangent classes are taken at certain like nodes or like mark points, right? So those are. So what are those? Those psi r plus i's.
So right now, I will tell you. Yeah. This is somehow the way I want to. At the m additional, basically, mark points.
Okay. Sure.
And then I move them by this relation in here. So this is some sort of an, if you really think about it, it's like it's translating elements of the cohomological field theory. If you apply it by T.
So,
in some way it's...
shouldn't your T be, shouldn't your T be an N to be? Like Z or? Your T will have to
Not
act.
really.
Your T will have to act on the cohomological class.
Mm-hmm.
Right? And it spits out another cohomological class.
I don't think so. Yeah, so you're not going to, for now at least, let me just state the theorem and then I need to make sure about this. So here is the given call. Telemon classification. Which is, it says fix some cohomological field theory omega, a semi-simple cohomological field theory with respect to that, and write, we can also write omega for topological part. Okay. The statement is basically that given any R matrix, I mean, the reason I'm not writing it as endomorphism is because this T you kind of construct from this R matrix.
Okay.
So let me actually show you,
Sure.
and then if it didn't make sense, then
Sure.
so given any symplectic R matrix, so this was the one that adjoint of R in variable minus C times R is equal to 1. Given any symplectic R matrix, we can form a power series So, given this way. Now let's just see if this makes sense actually. Z times 1, R of 1, so you plug in 1 of 1 and V into R. And this is basically what you have.
So
it will be, if I plug in 1 of V into this thing, then it becomes a power series in V itself, right?
I agree. Yeah, sure. Okay, so
and I'm removing this free element Z. So that was R was Z plus the power series endomorphism of V. with coefficients in endomorphism of E time in the
That's right.
power series of Z. So I'm removing that element, and I can construct this thing.
Sure.
Okay, and because this is 1 in V. Then becomes an honest power series in that. Then this Eventhal-Telemon classification says that there exists a unique matrix R for which, now let's see if this makes sense. Omega is R T omega. And it's remarkable, isn't it?
Just trying to parse it.
But this is the topological field theory, only spanned by degree 0 classes. This kind of thing is kind of translates these classes in the, let's say in cohomology theory of, if V is the cohomology theory of variety, and then the statement is that your cohomological field theory for all classes is given by this. There's always a unique R matrix which can do this for you.
So your T
Which is pretty remarkable.
Your T is from a symplectic R matrix.
That's right.
So what is this saying? You take your omega, you pick a random symplectic R matrix.
There's always a unique. It says there's always a unique R matrix
Such that
such that this statement is true.
Such that this statement, but your T depends on the R.
That's right.
Okay.
That's right. Given fixing omega. Okay, so I should have said. Okay, so maybe I should have said it this way. Fixing omega, there exists uniquely an R matrix, and T as above, such that this, or there exists a unique R matrix for which that this is correct. Yeah, I actually wrote it, so. Yeah.
Okay.
So for any given symplectic R matrix, you can construct some kind of power series like that, and then if you fix omega, then you can always realize omega as RT times topological field theory for some unique R matrix.
So basically,
Yeah.
omega is, you can recover the entire omega from your TFT part.
Yes. That's right. That's the classification.
Then I still don't understand what it means to say T acting on psi R plus 1. Because T then right now is a genuine power series in V, right?
That's right.
And those psi elements are also cohomological classes, right? So they're in V itself. So how do I?
So, but if you use this definition for T, does it make sense? Let's.
Well. No.
No. This is realized as endomorphism of V, but when we evaluate it at identity of V.
Yeah. This.
Let me make sense of that later.
Sure.
Yeah, the answer is I don't know, quite honestly. Yes, you're right, actually. This doesn't.
If V comes with a product, then it's
Yeah.
in our case, no. In general, for cohomological,
Let's look at the
Sure.
Giventhal's formalism.
In in general, V doesn't necessarily come with the inner product, right?
No.
So I'll just look it up.
No, but cohomological field theory does.
No, the V.
No.
No, it doesn't, right? So like,
Mm-hmm.
so I can't quite make sense of that. I suppose given Untitled is. Which paper is that? Is that the? Do you know the name of that paper?
What?
Do you know the name of
You just look at
this one? No.
semi-simple. So let's just look at actually this paper.
This
Right?
one?
Pandey and Schenk. Let's go to his.
Oh, archive changes.
This one?
This one?
No. Yeah. It's okay. That one. Let's see how do they define T. They go down. This is topological field theory. This is R matrix. This we did.
Yeah, so far it's fine. Not here. So. Still this part.
Doesn't make sense.
Yeah, no, this. Yeah,
It's a bit confusing.
This makes sense. I can go like chase down that part paper.
Yeah. Okay.
Sorry,
Yeah.
because I'm late. So what was the definition of cohomological field theory? It's a function or something to something.
Yeah. So you have some vector space. You fix an underlying field, algebraically closed field of characteristic 0. On this field, you have an algebra. Let's call the field K. You have a K algebra, commutative K algebra, like this. So you have this commutative K algebra A, and then you have some free.
This is fixed.
That's right.
Choose.
So you fix a free A module. So you have this A module, like that.
So that's your B.
Yeah, that's my V. And you also need to equip this with a non-degenerate pairing. So you have something like V tensor V onto the ground field. Okay, so let's wait for him to find the proof. Meanwhile,
you should keep going, but at the same time I can change.
Okay, so that's your V. And then cohomological field theory is a set of classes. It's a system of classes like this, where
What is the label?
omega GR.
GR.
And I will define what those are.
Some
Such that 2G minus 2 plus R needs to always be bigger than 0. And the way these are defined is that omega GR belongs to cohomology theory of your M bar GR with coefficients in this K algebra A, tensor with your dual of V R full tensor product. This is what the cohomological classes are. So in some sense, you have marked curves with R markings. You associate elements of V to these markings. And for every element of V, you associate to that a class. So, how should I say? You associate a class to this pairing the elements of V with the R markings, with markings on the curve. So think about Gromov-Witten class. Think about Gromov-Witten class, R-pointed Gromov-Witten class. You have a curve with R-marked points, right? This curve is supposed to pass in an ambient variety through certain cycles. All right, so those are the insertions, right? For every marked point, you have some cohomology class that you attach to that marked point. So now you have, let's say, R many cohomology classes. You pull them back to the moduli space of stable maps. You push them forward via the forgetful map onto the moduli space of pointed curves. That gives you a class. And that class is the Gromov-Witten class. So these are similarly defined, except here in our Gromov-Witten theory story, this is the cohomology theory of our variety X. But this is just defined for any free module over this K algebra. So this is more general than that, but it has a specialization to Gromov-Witten theory.
It's not. Probably. I'll just ask it this way. So, is this setting fitting to this Atiyah definition, topological field theory things, like a functor from?
Well, I don't know what that definition is. So.
You don't know that.
Yeah.
It's not obvious.
Is there any other example of like a cohomological field theory other than Gromov-Witten theory?
For instance, actually, there are many other examples. So for instance, the one we are going to do.
Oh, sure. Sure.
We are not just using the cohomology theory of X. We are doing, for us, this V will be the focus space on the Hilbert scheme of points. It's a.
Oh, I see. Okay. Yeah.
So do you remember what I'm talking about? This we covered many sessions ago. So we had this thing. And we had the forgetful map onto here, and we had the evaluation maps to X times R, X to the R. So you pick R many classes, you look at their tensor product, alpha 1 all the way, or V1 tensor all the way to VR, and you push them over here. And you will get one of these guys.
So this set of data, you said capital omega.
Yeah.
So you call it cohomological field
Yes.
theory.
So in the Gromov-Witten theory case, this omega GR is actually defined by, if I call this one rho, and if I call this one evaluation. So this is defined by rho lower star of evaluation upper star of V1 tensor VR capped with, because it goes up there, actually.
Actual fundamental concept.
Exactly. And that's what we did before. So this is more general than that. This is just any free A module. So it's a cohomological field theory so this way, it's a system of these objects taking values in here with certain axioms. So there are 3 axioms that they need to satisfy. The Lewing property, and they have associativity, and there is an identity element and so all that. Okay? And it's very similar to axioms of Gromov-Witten classes. If the axioms are satisfied, this system is called cohomological field theory, often with a unit. And the unit we had before, similar to the fundamental cycle, for instance. And this cohomological field theory, this system of classes, actually induces a certain notion of product, this time on V. Before, via Gromov-Witten classes, we defined the notion of quantum product. It was defined on the cohomology theory of X, the variety. Here it's just a V. But similar to before, these are analogs of Gromov-Witten classes. Similar to before, these things induce a notion of quantum product on V. And again, with respect to that product, this V takes the structure of certain Frobenius algebra. Yes. And this non-degenerate pairing for us before was the intersection pairing. Here it is some non-degenerate pairing, which we define. So you fix this data, V and eta, and the identity or distinguished element of V, and this is enough to construct a cohomological field theory. Yes, and then this part is if you just span degree 0 cycles. So these are taking values in here, and if you just look at degree 0 cycles, these are, we call them omega GR. And this system of omega GR, where for these classes you just look at degree 0 cycle, I mean, it's way more general than the Gromov-Witten class, right? So here it's just a specialization to Gromov-Witten theory, but I can have degree 0 cycles. The Gromov-Witten classes, the degree of the Gromov-Witten class you can actually calculate, right? So if you use, this is, you don't have any, you have flexibility on the degree here actually. So if you just use degree 0 cycles, let's say, then these are called topological field theory.
All right, so in this general cohomological field theory, only a larger space of curve with not points involved.
Yeah.
The stable non-larger space, not necessary.
No, not necessary. No. When you specialize to Gromov-Witten theory, the class that you will get here has a specific structure, which is actually given by capping with this one. And so you can actually calculate this degree. Yeah. That's way more general than just Gromov-Witten theory. And then Giventhal and Telemann actually give you a certain classification of these things. So they say that the cohomological field theory is related to topological field theory. So from degree 0 cycles, from these guys, you can construct these guys via this operators that act on the cohomological field theory, this R matrix and T matrix. They induce certain actions on your cohomological field theory. Yeah, and your statement is that there's always a unique R matrix that you can find, and your cohomological field theory satisfies RT omega. Except now, right now, actually, we are wondering about certain meaning of one of these terms that I've put in here, but yeah.
I'm almost there.
Yep.
I'm almost being able to. It's a little bit hard to parse.
Yeah.
It's a little bit hard to parse.
Yeah, this is why I told you guys you need to help me.
Yeah. No, I'm almost there.
Anyways, but we are learning, so it's okay. All right. Okay, so this is the classification. Let's see. So while he's finding it, so let's discuss about cohomological field theory for Hilbert of C2 and symmetric end of C2. So the cohomological field theories determined by T equivariant Gromov-Witten theory of Hilbert of C2 and symmetric end product of C2 are determined by underlying algebras A, the algebra T1, T2. These are again equivariant parameters in equivariant cohomology theory of C2. This is a power series with coefficients in the polynomial ring in T1, T2 with coefficients in Q. And A tilde will be Q T1, T2 power series in formal variable U. So this is what we're going to do. We're going to look at cohomological field theories associated to Hilbert and cohomological field theories associated to symmetric N.
I start to think maybe that when he wrote R and T with evaluating on the potential class, it seems like he's plugging potential class into Z. That is what it seems to be.
It is possible, yes.
But I'm trying to figure out, like, then.
However, then what does it mean having?
So it still doesn't make sense to me. Well,
Why is it the power series, basically?
Well, convergence issue aside, the problem is like, so I have like T something, T2 Z squared T. If I plug in a particular, then it still requires me to have a product on. Wait, sorry, just. You probably should keep going. I'll just have to think a little bit about this. Looks a little bit weird to me. But
It could be actually some sort of.
I think that's what's going on.
Yeah. Because we have already evaluated this R at one of the endomorphism, so
Right.
it could be. That's the only possibility. No?
Yeah.
So here the corresponding free module is given by V. This is f of n tensor with A over Q and V tilde f of n tensor with A tilde over Q. So this is the free module we associate to this guy for Hilbert and the other one for symmetric N. Okay? And these are the focus spaces. So both of these guys are focus spaces with basis indexed by partitions of this integer n.
That symmetric product is a singular space, right?
What?
That symmetric
Yeah.
product. The Gromov-Witten theorem, it is well defined.
Orbifold Gromov-Witten theory. So there is actually a statement that you relate the two Gromov-Witten theories together. That's one of the theorems. Here, the inner product. Yes, actually you're right. It is the Z. That's the only possibility. It will converge. Like, I mean, the convergence of this thing is actually immediate because you run out of.
But what it doesn't mean, like okay, so where is the potential class? The potential class is
in the certain cohomology theory of your variety.
right. So I have to be able to multiply like the element of my V, which is, I mean, I do in this case. I can multiply cohomology classes, but that
You're
would
copying it.
huh?
You're just copying them, right?
Yeah, I know, but like that would stipulate that I need to have a product on my V. Because this V is not just a like this V is not just a module over my base ring, right?
No, of course, you always have this non-degenerate pairing defines the product, the structure.
Oh, right, okay. Right, the non-degenerate pairing defines the product.
Yeah, I mean,
the product goes to the base
for
ring.
instance, for cohomology theory of X, the product to structure is Gij. The regular product to structure is just Gij, intersection pairing.
Oh, okay.
That the non-degenerate pairing for you is an extension of the Poincare pairing.
Right. Sorry, just one second. So this non-degenerate pairing, you're saying this non-degenerate pairing gives you a product structure by what? Oh, I think I know what you mean now. Okay, so you're saying that I declare that my EI like intersect cup EJ is the same thing as what? So
Yes, it is the same as if you look at. It's exactly like how we define.
Yeah, so how does the intersection pairing work again? So I have a.
So we had the EIs,
Right.
and we could raise the index.
Yeah.
For everyone, we had the dual basis, and that was basically GKI. So let's say EI,
Yeah.
EK.
Mm-hmm.
This was giving us the product structure,
Right.
one of the product structures on cohomology theories, cohomology theory of your variety. Now you just replace this with this non-degenerate pairing, and you have an inverse matrix. So this guy, you think of as this.
Yeah, I'm just trying to recall in the intersection product pairing one. How do I multiply two? How do I cup two? Say I have EI and EJ. How do I cup EI and EJ? EI and EJ.
So for the intersection pairing, you were taking the.
I'm just
Poincare dualize and then intersect.
Poincare dual, and then intersect.
Yes.
Yeah. No, I'm just trying to say, like, in terms of that matrix alone. Like, if I only had the data of GKI. So just give me one second. I think this is immediate. Oh, I understand. Okay. No, it's all good. No. It's fine. You just read off the interest of it, I suppose.
Yes, that's right.
Yeah, okay.
The entries are the intersection.
You just read off the interest. Okay. Yeah.
Yes.
Yeah.
I mean, that's what it means, right? I mean, I'm describing the intersection product with its matrix elements. That's what I meant it. Yeah.
Yeah. I'm all good.
It's okay. Yeah. So here the inner product, and you see again the inner product structure here for the focus space. This is defined as eta of mu and nu is going to be inner product of mu nu, which we had before on the focus space, and this is defined as -1 to the length of mu minus length of the partition of mu. I mean, mu is a partition, right? Delta mu nu, T1, T2, length of partition mu, and this thing which keeps track of the automorphisms. This we have done before. It's just trying to say that, well, if you use Hilbert scheme of Hilben of C2 or Hilben, your intersection pairing will be the intersection pairing defined in the focus space.
By the way, the N here is the same as a like a pure N.
That's right. It's the focus space associated to Hilben.
But the focus space itself involves all N, right? You have to take all the cohomology with different. So actually that data is not just for one N.
That's right. This is one of the factors for one Hilbert. We discussed this before, actually.
Oh, I probably missed
The whole Fokker space is defined is actually infinite sum of the
Yes.
cohomologies of Hilberts, and this is for one of them. So on each one of the Hilbert schemes, basically your cohomology classes are being indexed by partitions of a fixed integer n. Yeah. So since both homological field theories are semi-simple, we obtain uniquely R matrices, which I call R Hilb and R sim n, sim, by applying Giventhal-Telemann classification. So every time you have a semi-simple cohomological field theory, it is generated by certain uniquely defined R matrix and T matrix acting on topological field theory. So it's a statement that we have here the same, because both of these cohomological field theories for sim n or for Hilbert, they are semi-simple. So we must be able to find uniquely these R matrices. Okay. Now remark there exists a linear transformation oh, by the way, this is for Hilbert. This is for Hilbert of C2. And for Simen, it is the same thing but without the sign. So for Simen, this thing is just without the sign. Okay. So there exists a linear transformation from V to V tilde defined by mu going to sending mu to the mu tilde, which satisfies which is given as follows. So basically you will see it's a linear transformation because the inner product structure intersection pairings with respect to eta tilde and eta are the same if I forget about this sign. So I can scale mu's in here with a sign and I will get the mu downstairs. So basically this I can do. Minus 1 to the L of mu minus mu. This is times mu. So here this is length of the subscheme minus L of mu. I'm dividing by this thing, and so this is what it is. Okay, and this is an element of V tilde on the Simen. Now there is a theorem that we are going to prove next time, which is due to Pandey and Schenk, which says for all g bigger than or equal to 0 and mu1 to mu r partitions indexed by this integer n for the Hilbert of C2, we have the following. Mu1, mu2, mu r on Hilbert of C2 for genus G is equal to mu1 tilde to mu r tilde on sim n of C2 for genus G. And this is after a variable change minus q equal to e to the IU. So this is the one that you were asking about. So quantum cohomology for genus G, quantum product, G-pointed function, G-pointed invariant, Gromov-Witten invariant on Hilbert of C2 is related to the one for sim n of C2, for the Hilbert. And this is actually essential in proving the statement we are going to prove. So we would like, our ultimate goal is to show quantum multiplication on the focus space for Hilbert of C2 matches with Gromov-Witten partition function. But this time R-pointed Gromov-Witten partition function and for all genus, G, for higher genus. This is something that we will use, and I will discuss next time. So let's just stop in here.
So why is this? So on the left hand you have this is the Gromov-Witten potential
For Hilbert.
For the Hilbert scheme.
And on this side you have this orbifold Gromov-Witten theory for.
You want to first match them.
Yeah,
and then
first match them and then
match that with the.
That's right.
The way you do it is match the matrix. Oh, also I found what I was missing. So what happened there when you have a power series? What they say is that you consider that as, so you have T evaluating on, let's say, some psi, right?
That's right.
What you do is you consider this like as sort of like a syntactic sugar. What it means is like you consider it as a big sum and you pull the cohomology class out of the expression. I'll just write it. It's easier.
Go right over there. Yeah.
Oh, yeah. So if you have, let's say T is like T2Z2 plus T3Z3 plus, and then this is VZ. When you evaluate on a